Okay, so we saw an implausible or a nonsensical Nash equilibrium when we did the example of player 1 choosing between C, D, and E, player 2 choosing between F and G if player 1 has played either C or D, and between H and I if player 1 is playing E. Go back to earlier videos if you don't know what I'm talking about. There was an implausible equilibrium there in which player 1 chose E, thinking that player 2 would choose G if player 1 had played either C or D. We want to get rid of implausible equilibria in this game, in these types of games. But we can't use subgame perfection, we can't use trembling hand perfection, we can't use any of the methods that we've described so far, so we have to come up with something new. In order to do that, we need to add to our language a little bit. The first thing is we need to specify a belief system. Now, because there is imperfect information, right, there are these information sets. What a belief system does is that for every information set, it assigns a probability distribution over the histories in that information set, right? So take the example of the previous game, the one where it was a simple card game, right? Player 2 has an information set in which player 1 has raised, yes, but we don't know whether chance gave player 1 a black card or a red card. The belief system would assign a probability distribution over that black card or red card, over whether player 1 has raised after observing a black card or raised after observing a red card. A behavioral strategy is, for each player I, it's a probability distribution over actions. This is different. There's a subtle difference between this and a mixed strategy. A mixed strategy is a probability distribution over pure strategies. So again, if you take the previous example, player 1's strategies were either RR, RS, SR, or SS, right? These were the pure strategies, and a mixed strategy has to specify the probability distribution over 4 actions. A behavior, so you need to specify at least 3 numbers, and you get the 4th one for free because all of those numbers will add up to 1, right? It's a probability distribution. You will play some action, you will play some strategy as player 1, so this and this probability has to add up to 1. A behavioral strategy, on the other hand, specifies what player 1 does if it's black. So percent of the time that player 1 raises if the card is black, and percent of the time player 1 raises if the card is red. And those are independent probabilities, and you only need to specify these 2 numbers in order to get the behavioral strategy. You have a perfect equivalence in all of these games. Like in all of the games we study, for every mixed strategy you can find an equivalent behavioral strategy, and for every behavioral strategy you can find an equivalent mixed strategy. It's worthwhile to mention that subtle difference. It's just mathematically more convenient to work with a behavioral strategy in this environment than with a mixed strategy. And assessment is like, it's a candidate equilibrium, sort of. It's a specification of both a belief system and a behavioral strategy. Not all assessments will be equilibria, but all equilibria have to be a combination of both behavioral systems, belief systems and behavioral strategies, and therefore all equilibria have to be assessments. In order for an assessment to be an equilibrium, the assessment has to satisfy 2 properties. One is sequential rationality, which means that an optimal strategy is played at every move. So every time player I has a turn, player I has to choose the optimal strategy. In the game that we first saw, the one where player 1 chooses between C, D, and E, and player 2 either chooses between F and G or between H and I, the equilibrium where you had E, G, H, that equilibrium fails sequential rationality because player 2 there plays G where player 2 shouldn't be playing G at all. So in that information set. The next thing we need is consistency of beliefs with strategies. So in, let's say, the card game, right? If player 1 only raises when player 1 has the black card and never raises when player 1 has the red card, if that's the strategy that player 1 is playing, then player 2's belief of what the history must have been when player 2 sees player 1 raise has to be consistent with that strategy. Okay, so whatever distribution of whatever behavioral strategy player 1 plays in that game, that will determine player 2's beliefs over what the history must have been if player 2 sees that player 1 has raised. In equilibrium, it has to be that player 2's beliefs are consistent with player 1's actions. They have to be consistent with all of the strategy profile, actually. So you can never have incorrect beliefs in equilibrium in this game in order for the assessment to be in equilibrium. Okay. This concludes the lectures for today.